Hi, my name is Kai Bailey, and I'm going to be explaining vectors and their application in physics. So first of all, we know that vectors are defined by their magnitude and direction, which can be represented by length and angle. Vectors are important in physics, and they're used in almost every single unit. And you can see them around you in your life, and you use them without even necessarily knowing what vectors are. In physics, we can use them to analyze objects in motion, like a car in motion, or we can use them to analyze bridges and the forces that keep them standing up. This second type is one we're going to be doing today, and it involves forces in equilibrium. So forces that cancel out, and the resultant force is going to be equal to 0. So in this example, we have a block sitting on an incline with an angle of theta. The weight is going to be W. The normal, this is the weight of the block. The normal is going to be the force that the plane exerts on the block, and the static friction force is going to be acting this way, parallel to the normal, perpendicular to the normal, and it equals the normal times mu of s. So, with all this in mind, we're going to try and solve for mu of s in terms of all these other components here. So we know it's an equilibrium. This means, as I stated before, that the sum of the forces is going to be equal to 0. From here, we can also say that the sum of forces in the x direction and the sum of forces in the y direction are both going to be equal to 0. In order to apply these two equations, we need a coordinate plane. So over here, we'll draw one with the x-axis and the y-axis here. This way, it's easier to analyze for the force of friction. Now we can start plugging in some of these values into these equations over here. So clearly, f of s is going to be acting directly along the x-axis. So when we sum the forces on the x-axis, we know we're going to have f of s acting in the negative x direction. And in the f of y direction, we know we're going to have a force acting in the y direction here, n. But what about this one? It's not acting on either of these two axes. So we can break it down into component form, and we can say that there's a component acting here in the x direction and a component acting in the y direction that are going to give the resultant here. We can get these two components with a little bit of trigonometry, and it comes out to be that the component acting in the x direction is going to be w sine of theta, and the component acting in the y direction is going to be minus w cosine of theta. Now we can begin to solve for this, and the first step we're going to want to do is solve for the normal. We can just rearrange this and say the normal is equal to w cosine of theta. We can also solve for the force of friction up here, and we'll find that f of s is equal to w sine of theta. From here, we know that f of s is equal to the normal times the coefficient of friction, and we can plug in this substitution here, w cosine of theta, for n, and then divide n over on both sides of this equation here, and we'll see that mu of s is equal to w sine of theta over w cosine of theta. The w's cancel out, and the sine and cosine are going to cancel out, and we'll find that mu of s, no matter what the weight is always going to be equal to the tangent of theta. I hope you guys enjoyed this video. If you want more information or want more complicated examples, you can take physics, That's all for this video. Thank you guys for watching.